Hello, my name is Mihir Yawakar, and I will be presenting today on rtCaptCha, a real-time CAPTCHA-based liveness detection system. First, I would like to acknowledge the authors of this paper, Erkam Uzun, Simon Pak Ho Chung, Irfan Essa, and Professor Wenki Lee, all of Georgia Institute of Technology. This paper was originally presented at Network and Distributed Systems Security Symposium in 2018 in San Diego. Let me give you a little bit of background on this paper. Facial and voice-based authentication methods are becoming increasingly popular and have already been adopted by customers like MasterCard and Alipay. As a result, big players like Microsoft Cognitive Services or Amazon Rekognition are becoming increasingly widespread. However, just as these services are permeating throughout the market, so too are vulnerabilities on these services. Recently, attackers have gotten very good at creating authentic video and audio of any target victim to impersonate them. Even simple attacks with a handful of pictures or voice samples of a victim are good enough to bypass some of these services. In this paper, researchers propose an alternative authentication method known as rtCaptCha, or real-time CAPTCHA. In this approach, a real-time CAPTCHA is sent to a user to announce via video and audio recording. As a result, an attacker must not only impersonate a victim, but manage to synthesize a real-time response to any given CAPTCHA in an acceptable amount of time. It is easy for an attacker to break existing authentication methods since the tasks are known ahead of time. Techniques exist that allow an attacker to fake tasks such as smiling or blinking and allow them to impersonate a user. As a result, these attacks can be scaled to large quantities of victims. Existing attacks can be broken down into two categories: presentation attacks and compromising attacks. Presentation attacks involve physically presenting the fake media, such as photos or masks, to the sensors used by the authentication system, like the webcam, while compromising attacks involve tampering with the input to the sensors themselves, with things like video recordings or 3D face models. Categorically, presentation attacks often occur in the real world, while compromising attacks can occur in the digital world. Most defenses on these attacks focus on making it harder for an adversary to generate good video of a victim performing the authentication task. Both types of attacks can be defended by determining the liveness of a user, or rather, if he can be treated as a real entity or not. Challenge response-based liveness tests, such as asking a user to smile, can be used, but these can be trivially broken. Researchers have instead focused on a more advanced technique like determining 3D structures, texture, or even the reflectance of human skin for presentation attacks, while for compromising attacks, analyzing genuine noise patterns, text challenges, or even audio CAPTCHAs can be used. However, these two are trivially broken, as synthesized voice samples can be easily produced. In summary, the contributions of this work are performing empirical spoofing analysis on current cloud-based audiovisual recognition, proposing practical and usable liveness detection schemes used by securing infrastructure with CAPTCHA, performing analysis on existing automated man-powered CAPTCHA breaking services and state-of-the-art CAPTCHA solving algorithms, implementing a prototype with Android applications and conducting a user study, and evaluating to show that the audio response of a normal human being to a CAPTCHA challenge is much shorter than automated attacks, which have state-of-the-art synthesizers and CAPTCHA breaking techniques. Researchers instead have proposed alternative solutions that combine the best techniques and practices from both trains of thought. They propose that instead of making it harder for an adversary to generate video of a victim performing a known task to fool an authentication system, they make it instead harder for an adversary to know what is the required task that the user must perform in order to successfully complete an authentication. In particular, at each authentication attempt, instead of asking a user to perform a simple action such as blinking or smiling in front of the camera on an authentication device, the authentication server will instead send the user a CAPTCHA and have that authentication device take a video of the user answering the CAPTCHA. For a normal user, this will be easy, but for an automated attack, this will mean automatically solving the CAPTCHA before feeding the answer into an algorithm for generating the fake video of the user answering the CAPTCHA. As in all CAPTCHA schemes, it can be assumed that the time it takes for a real user to solve the CAPTCHA is significantly shorter than it is for the adversary. As a result, a user should only be authenticated if a correct response is responded in a threshold time. Researchers studied how vulnerable popular facial and voice authentication systems are to the aforementioned attacks in order to study how they should implement rtCAPTCHA. They tested adopted cloud-based facial recognition services that were implemented by major companies such as Microsoft, Amazon, Alipay, and Kairos. Each system was studied against videos with both real and fake faces. Genuine videos from the CAPTCHA face anti-spoofing database were used as positive samples and then also used to synthesize fake samples. Three main techniques were used to synthesize fake samples from the real ones. First, 3D face models from genuine videos of the subjects were created by using three different tools: the Surrey face model, an open source tool called FaceGen, and a demo version of an enterprise tool called CrazyTalk. Some of these tools even put branded watermarks on the fake samples, but researchers claimed that this had no bearing on the results. Second, cartoon and sketch photos were generated from the real samples and tested against the authentication systems. Finally, fake eyes and mouths were placed over the correct features onto the manipulated faces of the subjects. The results from this initial testing were actually quite alarming. As part of the experiment, baseline performance metrics of each services were extracted. A genuine face from an enrolled user was presented to test the true positive results, while a genuine face from a non-enrolled user was presented to test true negative results. Researchers found that there was an overline baseline true score of 100%, while an overline baseline true negative score of 95% was present, with 86 and 76% overall confidence rates respectively. Of the services, Amazon Recognition performed the best. However, results also showed that a whopping 93% of spoofed faces were detected as genuine copies. So why did this happen? Cartoon and sketch photo attacks showed that texture information was not considered in the authentication process for these systems. Fake facial feature attacks proved that these systems use only the location of facial features rather than try to actually match them to their known points of reference. Finally, even 3D face models with watermarks were accepted as legitimate users, proving that even rough frame manipulation on facial videos could trick liveness tests, such as being asked to blink. Automatic speaker verification systems were also shown to have similar vulnerabilities to attacks like their facial recognition counterparts. Synthesized voices were used to attack the Microsoft Speaker Identification Service by using open-source synthesized speech datasets. The ASV Swooping Challenge and DNN-based speaker adaptation work by Wu was used to synthesize these voices. Both genuine and synthesized samples for one female and one male speaker were used to synthesize and generate fake speech samples. For genuine enrolled users, 97% of the samples were identified correctly. Synthesized samples had a 65% chance of being identified as genuine, however. More so, in some of the DNN-based approaches, up to 100% of the speakers could be synthesized for positive spoofing results. A high-level flow of the rtCaptCHA approach that researchers proposed can be described as follows. The process starts when a device like a mobile phone needs to start an authentication or registration session. When the authentication server receives such a request, it will generate and send a CAPTCHA challenge to the authentication device, and then measure the time until the authentication device responds. The session will time out if no response is received after a predefined period. On the device, once it receives a CAPTCHA challenge, it will display the challenge to the user and start recording the user's audio response. A client app on the device will also take a number of snapshots of the user at random using the front-facing camera on the phone. The phone's voice recognition system can determine when the user has finished responding to the CAPTCHA challenge, and then the app can then proceed to send the captured data back to the authentication server. A standard speech-to-text algorithm is then used to determine whether the audio sample gave the correct CAPTCHA solution. It is also determined how long a user took to start responding. If a user took too long, the authentication request can be rejected. An authenticated user's samples are then compared to samples that were taken when that user was first enrolling. The first part of the validation of the face and voice samples received for rtCaptCHA is to transcribe the voice samples using a speech-to-text algorithm to see if it's a correct answer for the set CAPTCHA. To do this, the open-sourced software CMU Pocket Sphinx library was used to do the verification on the mobile devices themselves. More sophisticated alternatives were also considered, like Baidu's open source framework DeepSpeech, or cloud-based cognitive services like Microsoft Bing API and IBM's Watson's speech-to-text services. The network latency and the overhead of some of these services were considered as drawbacks for this research, however, and not used. Next, the user response time was measured. Research found that audio responses for CAPTCHAs are answered by users much quicker than text-based responses, meaning that the window of opportunity for an attacker is even smaller than normal. Speech activity detection was classified using a multi-layer classifier with an error rate of around 2% to determine genuine response times. If the time was within an expected human's response time, but not longer than the breaking time of that corresponding CAPTCHA scheme, the response was marked as a genuine attempt. Finally, the last data verified was the user's facial and voice data by using data from the registration phase of the authentication flow. To test out and evaluate the new authentication flow, a user study was held. An Android app was created to experiment with 5 different challenge response-based liveness detections. Each user was tasked with reading out loud numbers, text that was presented on the screen with different CAPTCHA schemes, or performing an action in front of the screen, such as blinking or even smiling. Some challenges were displayed by animating the challenge on the screen as to prevent simple frame analysis on the request from an attacker. For the smiling and blinking methods, Google's Mobile Vision API was used to determine whether the user was smiling or blinking. Overall, 31 volunteers tested out the app after being shown an introductory video on how to use the app and how to perform the tasks. Each participant was asked to answer 3 rounds of challenges for a total of 15 different challenges each. A timeout value of 10 seconds was considered as a failure. An example of what this app looked like can be seen on the screen. The results of the study can be summarized as follows. As a baseline, 89% of CAPTCHA challenges were answered by participants correctly with an average response time of 0.93 seconds. This baseline is considerably more accurate and faster than any known existing CAPTCHA breaking schemes. Also, 100% of participants' faces and voices were verified with high confidence levels. It was shown that the minimum time to give a smile or blink response is higher than the largest measured response time of any of the CAPTCHA-based challenges. This was probably due to the fact that larger samples of frames are necessary to actually determine whether a user is blinking or smiling. Additionally, there was no significant difference between challenge response times between participants, nor was there any discrepancy in accuracy amongst them. Results showed that for a given participant, response times remained constant for various CAPTCHA schemes. Results also showed that numeric-based challenge CAPTCHAs were slightly more accurate than English phrase-based ones. It is worth mentioning that there was a slight warm-up effect delay for some of these tasks, meaning that the first task of a set took longer than the other ones. Finally, since a user was asked to retry in the event of a failed authentication, data showed that it took at most 2 attempts for a successful authentication. Researchers analyzed how likely it was for an attacker to break their rtCaptcha scheme. They assume an attacker can compromise the victim's phone kernel, that an attacker can have a malicious version of the client app used for authenticating with rtCaptcha, and that an attacker can also use the victim's phone camera and microphone to collect face and voice samples to build models for the face and voice. They concluded that the main obstacle in achieving successful authentication is to solve the CAPTCHA before the authentication session times out. The goal of an attacker is to solve the CAPTCHA, create a facial and audio model of the victim, and then create a video and audio track of the victim responding to that CAPTCHA. Thus, the key to an attacker's chance of success depends on the threshold for session timeout, or TH-legit. To summarize, the strength of rtCaptcha depends on the difference between TH-legit's threshold, that's long enough for a legitimate human user to have a good rate of success at authentication, versus the TH-legit's threshold that allows for accurately breaking CAPTCHAs using a CAPTCHA breaking technique. In the user study, participants responded to 98.5% of challenges in less than 3 seconds, with an overall accuracy of 87.1%. Thus, legit was assumed to be 5 seconds to give a reasonable room for error by researchers. An attacker's chances of breaking rtCaptcha under 5 seconds were evaluated. State-of-the-art CAPTCHA breaking techniques were first evaluated from Gao and Bernstein, which used reinforcement learning techniques. Yandex schemes and even other primitive optical character recognition techniques were also evaluated in solving the CAPTCHA challenges themselves. Even the most sophisticated techniques took longer than 3 seconds to achieve a believable accuracy score. Thus, researchers are confident that a threshold of 5 seconds was sufficient given all the other requirements of rtCaptCha. However, the security of rtCaptCha still directly correlates with the security of CAPTCHA itself, which is shown to be resilient to advancements and the upper bounds of its solving times. rtCaptCha is shown to have other security benefits as well. Researchers note it is very difficult to capture the user giving out the answer to rtCaptCha correctly just by accident. Other liveness-based tests such as smiling or blinking are more vulnerable to attacks due to an attacker's ability to drive towards a legitimate authentication. It is possible for an attacker to cover up the phone's display with an overlay so that the user doesn't know that they are currently being attacked. With this attack, success is more likely because people naturally blink and naturally smile more often, and thus they can unknowingly provide the answer to the underlying challenge and help the attacker to authenticate. rtCaptCha, on the other hand, is somewhat resistant to these attacks, as it's highly unlikely that the victim will spell out the right CAPTCHA by accident. Researchers also noted potential improvements on this study. Reaching a big diversity in the user study was a big limitation. Recruits consisted mainly of university students who were more familiar with the technologies that backed rtCaptCha. They think it's worth experimenting against populations who are less technologically savvy or unfamiliar with CAPTCHAs themselves. Researchers also highlighted the need to evaluate the robustness of the used speech-to-text algorithms, as it's a core aspect of the rtCaptCha authentication scheme. The collected data in the user study involved ambient office noise, restaurants, outside environments with AC sound, small hums and buzzes, and light traffic sounds. However, this is still limited in variety, and it's worth evaluating how larger differences in noise can impact CMU's Pocket Sphinx library and some of the aforementioned other techniques. Moreover, recent advancements in lip reading techniques could also lead to more accurate usability and performance of rtCaptCha. Current lip reading techniques have an accuracy of around 95% for sentences with only video-based feedback. Researchers hope to test out the viability of such lip reading techniques for rtCaptCha moving forward. Finally, due to the nature of rtCaptCha, a user must present genuine muscle movements to perform the authentication tasks. For an attacker wearing a mask in a presentation attack, incorporating such muscle movements is next to impossible. Coupled with lip reading techniques, researchers want to evaluate the impact that rtCaptCha has on thwarting such presentation attacks. In conclusion, rtCaptCha aims to help strengthen existing flaws in liveness detection systems. Research shows that a $15 billion market for cloud-based cognitive services could be served by rtCaptCha. Spoofing techniques make some of these existing services extremely vulnerable to attack. However, CAPTCHA-based techniques have shown that success for almost a decade now, and so rtCaptCha can be backed by that same extensive security. Results have shown that even the most advanced, state-of-the-art CAPTCHA breaking techniques are not sufficient enough to break rtCaptCha, and so the way forward is very promising. rtCaptCha is definitely a viable alternative to existing techniques. Thank you for your consideration. Finally, I wanted to highlight the relevance of this paper and rtCaptCha's significance to our class. Authenticity in the physical space is just as important as authenticity in the digital space. We have things like digital signatures for the digital space, but often rely on various biometric techniques for the physical spaces. Users can ultimately access every system in things like CPSs, and so it's important to determine which users should be accessing what devices. However, without reliable authentication schemes like rtCAPTCHA, security systems like this are thrown out the window. Remote terminals that require authentication are especially susceptible to presentation attacks and often cannot be backed by other security measures. rtCAPTCHA can be potentially extended to serve system components such as these and other various results